Hello everyone, today we're going to be working on example 4-7 and this example is asking us to replace the loading system by an equivalent resultant force and moment acting at point A. So here we have our point A right here. As you could see, we have the force of 40 newtons, 30 newtons, and this force at 50 newtons going diagonal. It's given to us that it has a slope of a 3, 4, 5 triangle like that. And we can't forget about the 200 Newton meter moment that is going on. So to replace the loading system by an equivalent resultant force and moment, the first thing that I'm going to do is I'm going to be finding the vertical and horizontal force of this diagonal force. So we're going to split that up into two parts. To find the horizontal force, we're going to multiply the 50 newtons by 4/5. And we do this because since we're trying to find the horizontal force, or yeah, the horizontal force of it, and we're working with the vertical force. So that will give you 40 newtons. Now to find the vertical component or force of that 50 newtons, we're going to multiply 50 newtons by 3/5, giving us 30 newtons. Now that we found the horizontal and vertical force to that force of 50 newtons, we can now proceed to finding the resultant moment, the equivalent resultant moment. So what I'm going to do first is I'm going to be writing down all of our moments that are going to be occurring. So to start off, we're going to start off with our 40 newtons. As you could see, these 40 newtons are they directly lie on this, since it's a vertical force, it lies directly on that vertical axis of point A, so we know that's not going to be creating a moment. So we could negate that one. Now we're going to proceed to our 30 newtons. We want, since it's a vertical force, we want it to align to that vertical axis of point A. So remember, moment is equal to the force times the distance. So we have our force, which is 30 newtons. So we just have to find our distance. Our distance is, since we have to shift it, we know that our distance is going to be 3 meters. Now we just have to determine if it's going to be a positive or a negative moment. Since it's going downwards, we know that's going to be creating a clockwise moment, meaning that's going to be a negative moment. So we end up getting that moment is equal to negative, he said 30 newtons times 3 meters, and that should give you negative 90 Newton meters going counterclockwise. So that means that we have positive 90 Newton meters going, sorry, I mixed that up. So this is negative 90 Newton meters going counterclockwise. That means we have a positive 90 Newton meters going clockwise. So now we're going to proceed to our 50 newtons that we have right here. As you can see, since it's a horizontal axis, it already intersects with that point, with that vertical axis. So that means that's not going to be creating a moment, so we can negate that one. From there, we have our 50 newtons going down, our 30 newtons that is going downwards. So we have our force, which is 30 newtons. Now we just need the distance. So we know that's going to be a total of 6 meters. From there, we just have to determine positive or negative moment. Since it is going downwards as well, it's also creating that clockwise moment, meaning it's going to be negative. So our moment for that one is equal to a negative 30 newtons times 6 meters. That should give you negative 180 Newton meters going counterclockwise. So that means 180 Newton meters going clockwise. And then from there, we just have our 200 Newton meters going clockwise as well. So from there, all we have to do is we have to sum all of our moments to get our equivalent resultant moment. So remember our sign convention? Counterclockwise is positive, so our resultant moment is equal to all of them, all of our moments that we found, as you can see, go clockwise, meaning they're all going to be negative. So we have negative 200 Newton meters minus 90 Newton meters minus 180 Newton meters, giving us a total of negative 470 Newton meters counterclockwise, meaning that our equivalent resultant moment is equal to positive 470 Newton meters going clockwise. So with that, we were able to replace the loading system by an equivalent resultant moment. So the only thing that's missing now, so we did this part, so we could check that part. The only thing that's missing now is the equivalent resultant force. So to do that, what we're going to do is now that we have all of our forces, remember these are our forces, 40 newtons, 30 newtons, 30 newtons, and then we have our 40 newtons right here. So we have to find an equivalent resultant force to that. So to do that, we only have one horizontal force, which is the 40 newtons. We know that's acting to the right. So we know that our sum of all of our forces in the x direction equal 40 newtons, since that's the only horizontal force. From there, we're going to just add our vertical forces. So I'm just going to move this down so we could work. Here we go. Move that. There we go. So we have the sum of our forces in the x direction. Now we're going to do the sum of our forces in the y direction. We have negative 40 newtons since it's going downwards, minus 30 newtons, again going downwards, and then again another 30 newtons going downwards. So we end up having a total of negative 100 newtons. So that means we have a total of 100 newtons acting downwards. So now that we have our sum of our forces in both the x and y direction, we will now sketch this out to be able to determine how we're going to solve for our resultant force. So we have 40 newtons going to the left. So let's draw our x and y axis. So this is our x-axis, this is our y-axis. As you could see, in our x-axis, we have 40 newtons going to the right. So we're going to have 40 newtons going to the right here. And then in our y direction, we have 100 newtons going downwards. So we have 100 newtons going downwards in our y direction. So we know that our resultant force is going to be somewhere around here in this quadrant. So since we know the sum of our forces in our x direction and our y direction, we can find our resultant force by simply plugging in our forces into this equation. So we end up getting 40 squared plus 100 squared. So we end up getting that our resultant force equals 108 newtons. But remember that when it comes to a resultant force, we also have to find the direction of that resultant force. So we're not done. We found the magnitude of the resultant force, but now we also have to find the direction of that resultant force. So if you could see here, we always want to start off with our positive x-axis. So what I'm going to do is I'm going to be finding our direction going counterclockwise from that positive x-axis. If you want to go clockwise, you know that this angle right here is equal to 270, since from here to here is 90, from here to here is another 90, and from here to here is another 90. So that's a total of 270, and then from there you would just have to find this angle and add that to 270. But I'm just going to be finding the direction going counterclockwise, so that just means I have to find this angle right here. So to find that, I'm just gonna close off right here the triangle, making a triangle. We know that this side equals 40 newtons. We know that this side is equal to 100 newtons. We know that this side is the same as this side right here. So we know that that also has a value of 100 newtons. And we're trying to find this angle. We'll call that angle theta. So we know the value of the opposite side of that angle and the adjacent side of that angle. And if you guys remember, tangent theta is equal to opposite over adjacent. That means that theta is equal to the tangent inverse of opposite over adjacent. So we input that into our information into that equation. So that means that theta is equal to the tangent inverse of 100 over 40, giving us that theta is equal to 68.2 degrees going counterclockwise from the positive x-axis. And now we have finished finding the equivalent resultant force, because remember in the previous steps, we found the magnitude of that equivalent resultant force, but we also had to find the direction. So this is our direction. 68.2 degrees going counterclockwise from the positive x-axis. So once again, this example was asking us to replace the loading system with an equivalent resultant force and moment that was acting at point A. We found that the equivalent resultant moment was 470 Newton meters going clockwise. And then from there, we found the equivalent resultant force. We ended up getting that the equivalent resultant force had a magnitude of 108 newtons, and the direction was 68.2 degrees going counterclockwise from the positive x-axis. Please feel free to like and subscribe to our channel if you guys would like to see more videos and content like this, and thank you guys for watching our video.